Assalamualaikum and hi. We are from Group 1 from AS120425. We have prepared this video for PHY380. So, in this video, we will talk about the evolution of X-ray, instrumentation, and techniques. As we can see here, these are our team members that contribute in these videos.
Without further ado, let's move to the introduction. German physicist Wilhelm Conrad Röntgen made the discovery of X-ray in 1895 while examining the effects of electron beams, also known as cathode rays, at the time in electrical discharge in low-pressure gases. Röntgen discovered a remarkable effect even when insulated from the direct visible and ultraviolet light of the gaseous discharge. A screen coated with a fluorescent substance put outside a discharge tube would glow. He concluded that the screens fluoresce because of an unseen radiation from the tube that traveled into the atmosphere. Röntgen was able to demonstrate that the radiation caused the fluorescence came from the location where the electron beam collided with the discharge tube glass wall. The new type of radiation proved to pass through opaque objects positioned between the tube and the screen. Röntgen produced a striking demonstration of this by taking a picture of a human hand spawn. Along with the discoveries of radioactivity and the electron, his discovery of what are now known as Röntgen's rays generated enthusiasm in both the scientific community and the general public, ushering in the study of atomic world and the modern era of physics.
The discovery of radioactivity 1896. So, Wilhelm Conrad Röntgen discovered that when electrons were accelerated by high voltage in a vacuum tube and allowed to strike a glass or metal surface inside the tube, fluorescent minerals some distance away will glow and photographic film will become exposed. These effects produce a new type of radiation which is we call as X-ray. So, what is X-ray? X-ray means an electromagnetic radiation of shorter wavelength than UV radiation produced by the bombardment of atoms by high-energy electrons in X-ray tubes. The first X-ray images by Wilhelm Conrad Röntgen. His earliest photographic plate from his experiment was a film of his wife Anna Ludwig Bertha's left hand with her wedding rings. This image was produced on Friday, November 8, 1895.
So let's see the advancement in X-ray tube. First, Coolidge tube introduction. William Lee Coolidge's invention represented a significant improvement over previous gas-filled X-ray tubes. The Coolidge tube produced X-ray in a more steady and controlled manner by using a heated tungsten filament as the cathode. It was able to produce continuous X-ray, which resulted in images that were more consistent and clear. This technology gained rapid ubiquity and stayed mostly unmodified through the 1950s. Secondly, advancement in Coolidge tube technology. In the 1920s and 1930s, improvements were made to boost the Coolidge tube's longevity and efficiency. Better vacuum technology and cooling techniques were among the innovations that made it possible to increase the tube voltage and currents. So now let's move to detection method. First, photographic plates. Photographic plates offer a direct way to take X-ray pictures, which was necessary for early X-ray detection. Clearer and more detailed photographs were made possible by advancement in photographic plate sensitivity and resolution during the 1920s and 1930s. Secondly, strengthening screen. Intensifying screens were introduced in the 1910s and saw substantial improvement in the 1920s and 1930s. Increasing the photographic plate's effectiveness, this screen had coating made of fluorescent materials, which when exposed to X-ray would release visible light, cutting down on exposure time and enhancing image quality. The diagnostic skill were enhanced when photographic plates and intensifying screen were used as routine procedure. Lastly, dual screen system. By the 1940s, two intensifying screens were placed between the photographic plate in twin screen system. What is the impact on medical imaging? Now, doctors could get better photos while exposing patients to less radiation, improving the accuracy of their diagnosis. Second, the foundation for further advancement in radiology and medical imaging technologies was established by this breakthrough.
For the next part is mid-20th century innovations for image-intensified tubes and digital radiography. For image-intensified tubes, it will convert X-ray into light image that hit fluorescent screen in vacuum tubes with non-limiting brightness. It was discovered in 1950 to focus on the brightness and improve the recent devices. So, X-ray beam will enter the body, then pass through image-intensified tube. Then, X-ray beam will absorb by fluorescent input screen to convert energy into light photons and strike the photocathode. It will emit photoelectrons, so electron from the photocathode then move towards anode, and guide to output phosphor and strike the electron to emit light photon that carry fluoroscopic image that can be seen directly by lenses or mirror or indirectly by closed-circuit TV. So for digital radiography, it is a technology that uses digital sensitive plate to capture X-ray image. It was invented around 1918, used digital detectors to have an image that are clearer and more details. Hence, it is easier to diagnose patients. So there are two types of detectors, which is direct and indirect conversion. For direct conversion, X-ray photon will directly convert into digitized electronic signals without using scintillator to ensure the sharper image can be formed. For indirect conversion, it will use a scintillator, so X-ray photon will be converted into electric charge with the presence of amorphous silicon photodiode matrix. So the image capture will available in digital form instantly. The next part is advanced imaging techniques for computed tomography, CT, and mammography. For computed tomography or CT scan, as we all know, X-ray examination that produce cross-sectional body image. It was discovered by Godfrey in 1960, who developed mathematical algorithm and theoretical that reconstructing tomography slice of human body from X-ray and keep improve from year to year to produce detailed structure and make an accurate diagnosis towards the patients. So the circular opening will rotate around the patients and the X-ray beam will produce narrow through the body. X-ray beam and detector rotate in opposite way at the same time. Then the X-ray at different angles will collected and sent to the computer to construct a cross-sectional image of body and will repeat the rotation to get a high resolution images and able to do detailed examine onto the patient. For mammography, it is X-ray test that used to detect breast cancer. It was started in 1913 by Albert Salomon to discover breast tissue. The technology advanced from year to year from 1950 until 1990, which produced better digital image of breast tissue to look for abnormalities. There are two types of mammography, which is digital mammography and tomosynthesis. For digital mammography, it uses solid-state detectors which can convert into electronic signal that can be stored in the computer. For tomosynthesis, X-ray that takes at different angles to get 3D images with lower exposure of X-ray beam, but the accuracy is low for certain type of breast. So the mammography is X-ray with a lower doses, so the patient's breast will placed between the plate, then pressed until it flat. Then the X-ray will pass through it. The detector then will transmit the signal to form digital image.
Alright, now let's talk about modern X-ray technologies from 2000 until present. Digital tomosynthesis, dual energy X-ray absorptiometry, which is we can call it AZHAR, synchrotron radiation, micro-CT and nano-CT. First, digital tomosynthesis. Digital breast tomosynthesis or DBT, also known as tomosynthesis or TOMO, was first approved by the FDA for clinical use in 2011. Full field digital mammography (DM) was widely accepted by that time, and it was hoped that DBT would improve digital outcomes. DBT consists of a series of small exposures obtained across an arc in relation to the digital detector that produce multiple slices at different levels in the image breast. These slices allow for individual images that are less encumbered by the tissue above or below, reducing superimposition. Because multiple exposures are made, each must be very low dose to keep overall exposure at acceptable levels. This limits individual in slice spatial resolution. However, image processing is available to enhance contrast resolution for a good overall result. Alright, next, dual energy X-ray absorptiometry, DEXA. DEXA or DXA uses a very small dose of ionizing radiation to produce pictures of the inside of the body, usually the lower or lumbar spine and hips, to measure bone loss. It is commonly used to diagnose osteoporosis, to assess an individual's risk for developing osteoporotic fractures. DXA is simple, quick and non-invasive. It's also the most commonly used and the most standard method for diagnosing osteoporosis. A single X-ray beam passing through the body will be attenuated by both soft tissue and bone, and it is not possible to determine from a single beam how much attenuation was attributable to the bone. However, the attenuation coefficients vary with the energy of the X-rays, and crucially, the ratio of the attenuation coefficient also varies. DEXA uses two energies of X-ray. The difference in total absorption between the two can be used by suitable weighting to subtract out the absorption by soft tissue, leaving just the absorption by bone, which is related to bone density. Another one, synchrotron radiation. Synchrotron radiation is a very bright, broadband, polarized pulse source of light extending from the infrared to the X-ray region. It is an extremely important source of vacuum ultraviolet radiation. Brightness is defined as flux per unit area per unit solid angle and is normally a more important quantity than flux alone, particularly in throughput limited applications, which include those in which monochromators are used. First observed in synchrotrons, synchrotron light is now produced by storage rings and other specialized particle accelerators, typically accelerating electrons. Once the high-energy electron beam has been generated, it is directed into auxiliary components such as bending magnets and in certain devices, undulators or wigglers, in storage rings and free electron lasers. These supply the strong magnetic fields perpendicular to the beam that are needed to stimulate the high-energy electrons to emit photons.
Now let's move to the future trends and innovations. The first one is photon counting detector. Photon counting detector is made of a semiconductor crystal which allow the detection of the incoming photons individually using a direct composition process. The spatial resolution is defined electrically and only limited by the charge distribution inside the semiconductor. This enables sharper image without the dose penalty of the interpixel gaps or post-patient collimation. The contrast to the noise ratio is increased by the detecting each photon individually with respect to its energy. This additional energy information can be used during any diagnostic procedure to get further detailed insight into the morphology and functionality of the scanned object. Emerging technology will providing higher resolution and lower radiation loops, potential to revolutionize CT imaging with improved tissue contrast and reduced artifacts. Now, the second one is AI and machine learning. The development and adoption of AI tools in radiology is growing rapidly. Embedding AI tools in imaging systems like mobile X-ray further helps to automate some of the technologies, manual tasks, and help provide reading radiologists with the new clinical decision support resources. To address staffing challenges, onboard AI tools can facilitate improved operational and reading workflows, supporting a more efficient clinical workflow and consistent imaging. Irrespective of the operator's experience level, AI tools can also help prioritize critical cases by detecting subtle or complex patterns within X-ray images, moving critical cases to the top of the reading list. Using these AI tools can impact improvement across the board in efficiency, quality, and clinical accuracy. Integration of artificial intelligence in image analysis and diagnostic will enhancement in image processing, anomaly detection, and workflow optimization. Now, the third one, which is the last one, is portable and handheld X-ray devices. Development of the compact and mobile X-ray system for use in remote and emergency setting, it will increase accessibility and convenience in various clinical and industrial applications.
For example, Penta handheld XRF analyzer for recycling and scrap sorting are IP55 rated to withstand rain, dirt, and dust and are drug tested using United States Department of Defense method to help prevent breakages and maximize uptime. Every Penta analyzer for scrap sorting is optimized with software features designed to improve return on investment and help scrap yards owners ensure consistent data captured across their device fleet. Each device comes with the innovative and proprietary Adzone technology so you get the right answer fast for high throughput and productivity. In conclusion, the evolution of X-ray, instrumentation and technique has been marked by continuous advancement and innovation. From the initial discovery and basic imaging methods to the sophisticated digital system and advanced imaging techniques of today, X-ray have become indispensable tools in medical, diagnostic, scientific, research and industrial application. The future holds promising developments with the integration of the new technologies and methods, further enhancing the capabilities and application of X-ray imaging.
Lastly, here is the list of references that we